All right. Hi, everyone. My name is Anne-Marie George, and I'm presenting joint work with Thomas, Meirav, Debabrota, and Christos on meritocracy in optimal set selection. So it's a relatively general framework, but I'm going to explain it on the case of college admissions. Just as a disclaimer, we've seen quite a bit of talks about school choice now, where we have matching problems. This is not a matching problem, it's a set selection problem. Okay. So what we have is a population. In the college admissions case, that is the list of applicants that we have. We denote that by N, and they come with features, X, that could be grades, gender, nationality, and so on. And we have a bit of uncertainty here about the outcomes, Y. That could be, for example, the success in their studies when we admit a student. And what we want to do, or what the decision maker, the EAAMO, wants to do, is to select a set of the population. Sorry, so that's the college's decision in this case, and we assume that they do that based on a utility function that they have, U, that depends on the set that we select and the outcome that they will get. So that could be based on diversity, the grades, the study success in general. Okay, and what we want to question is this fair? So if the decision maker is purely wanting to maximize their utility function, is this fair? Or in this talk in particular, we ask, is this meritocratic? I'm going to talk a bit more, or quite a bit more, about what meritocracy actually means and how we can define this in a minute. Just to point it out, this is a relatively general framework for set selection. We can imagine other scenarios like hiring a team of engineers for some particular project, or selecting a portfolio of algorithms that have different features. And I did mention that we have some uncertainty here over the outcomes. And so what we really want to look at is expected utility. So where we have a probability of outcomes occurring. So we can then define the expected utility given a selected set over the probabilities of outcomes. And our focus here is not to try to approximate these probabilities of outcomes occurring. We just assume we have them given or some approximation of them. And then we want to look at admission policies, pi, that could be deterministic, so saying basically we select a set, or stochastic, saying we select that set with probability something and another set with other probabilities and so on. And then we look at the expected utility given a policy. So that's basically just the sum over the possible sets we could select and the probability of selecting them times the expected utility we would get from that selection. Okay. So now we have a utility maximizing decision maker. So they want to find a policy that maximizes their expected utility. And we ask ourselves, is this meritocratic? So let's see what meritocracy actually is. So the Cambridge dictionary defines meritocracy as a social system, society, or organization in which people get success or power because of their abilities and not because of their money or other social position. So here, this ability, or what we call merit, is really a key notion. And this definitely depends on the context in which we want to make that selection. So we assume it depends on the decision maker's utility. And typically it's an intrinsic measure of worth of individuals. But what we want to focus on is a measure of worth that is kind of dependent on who else is selected. So that's probably best explained in a hiring scenario where we have a specific project where we need different skills, and so hiring a person or their worth towards the team is really dependent on who else is in the team already. Okay, so we have a utility function over sets of individuals that is in particular not necessarily linear. So we can't just add up the worth of every individual. Okay. And what is typically done in this kind of situations, or what one could do, is to look at Shapley values as a measure of merit. Let's quickly review what the Shapley value is. So for an individual J of our population, we look at the contribution that would give us in terms of utility. So we sum over all possible sets and look at the difference of what happens if we would add J to that set or not. And we weight that by some factor that is dependent on the size of the set. So that's really just a normalization. So that's a very nice measure and a very popular measure. It has a characterization with some desirable properties. I'm not going to go too much into this now. But let's look at what would happen if we were to use Shapley values. So here we have a scenario where we have 4 individuals and we want to select 2 of them for some task that they're supposed to perform. So we can see the utilities in this example on the edges and just assume that any set that is larger or smaller than 2 will have utility 0. Okay. So we really just want to select 2 of them. Okay, so we can compute the Shapley values. I guess you just have to believe me that they are like this. So Lucy would get a negative value and Charlie a positive one, and then Linus and Snoopy, I have the same value of 0. Okay, so if we wanted to be meritocratic and take the Shapley values as our measure of merit, then we would probably design a policy that kind of gives Charlie the highest chance of being admitted or selected, Lucy the lowest, and then we're kind of indifferent between Linus and Snoopy, right? Okay, but well, now that we know that we want to select Charlie and not Lucy, is it then really fair to look at the contributions that Snoopy has towards Lucy in the same, or weighted the same as the contribution Snoopy has towards Charlie, right? We're suddenly not indifferent anymore between Linus and Snoopy. We know we want to select Charlie and not Lucy, right? Okay, so if we always take Charlie and never take Lucy, then should we really weight all the contributions equally? Okay, so this is where we're coming from. So what we're going to do now is to define a different measure of merit that looks quite similar to the Shapley value, and we call that the expected marginal contribution. So this is dependent on the population that we have with their features, x, the expected utility function, and a policy, pi. Okay, so we already assume we know how we want to select things, and then we see what is the merit of taking someone else in based on that policy. Okay, so again, for every individual, J, we define the expected marginal contribution, so EMC of J, with respect to that policy and the utility function by summing up over all the possible sets that we could select and seeing what contribution to the utility J would have. So we look at the difference of utility when adding J versus not adding J. And this time we weighted by the probability of actually selecting that set. Okay. So that's again some form of a normalization. And we can see that this is actually a generalization of the Shapley value. So in particular, if we were looking at a policy that is egalitarian in the sense that we select a set purely dependent on the size of the set in some way, we get exactly the Shapley value. Okay. All right, so we now have a measure of merit that is dependent on a policy. But we want to define, okay, so first of all, that also satisfies some nice properties. Not going to get too much into this. This is not a characterization like we have for the Shapley value, but some of the properties are satisfied as well. Okay, so now we want to define what is a meritocratic policy with that measure of merit that is already dependent on policies. So we're going to do that based on 2 principles that are stability criteria. And the first one is what we call swap stability, where we say that, well, everyone that kind of got a higher chance of being admitted than me must somehow been more favorable in terms of expected utility than me. So someone else gets a higher chance must mean they also had a higher merit somehow. And the second principle is local stability, where we say, or if you would select, if I'm not selected with certainty, then doing so would probably decrease the utility. Okay. So that's a justification of why I don't have higher chances of being selected. Okay, so let's look at this in more detail. So the first criteria is swap stability. We say that we look at two individuals, I and J, and if we assume that I has a higher probability of being admitted than J, then that would mean formally that the utility of a policy where we force I to be admitted and J to be rejected would be higher than of a policy where we force J to be accepted and I to be rejected. Okay, so we can link this back to the EMC, the expected marginal contribution, say that if I and J were both rejected, then, well, I's contribution should be higher than J's contribution. And that's why we gave I a higher probability. Okay, for the second stability criterion, we looked at local stability. So we said that, well, the utility of a policy should be higher than if we were forcing I to be admitted. That's a justification, again, for not giving I higher chances, really. And again, we can link this back to the EMC, saying that this means basically for every individual, their contribution to the policy is non-positive. Okay. So we analyzed what this means, and we looked at, well, we want to focus on utility maximizing policies. We found that if we look at deterministic policies that select one set with certainty, and they are utility maximizing, then we actually find that they're also meritocratic, which is nice. This is not the case if we have a stochastic policy. Okay, but this is not the end of the story. We wanted to look at different policy structures. So very often in real life, we have policies that need to kind of be explainable to people, right? So we're not completely free in choosing any policy we want. So we looked at two types of structures that are separable policies and threshold policies. So for separable policies, we have parameterized policies with parameters theta, so that's a vector of parameters. And we say that the probability of an individual to be accepted really depends only on one of these parameters. And we can tune these parameters how we like in order to maximize our utility rate. In particular, we looked at softmax policies, which are popular, and linear policies. Where really the probability of someone being accepted really depends only on this parameter. And then we looked at threshold policies where, as you can expect, we have some form of a weighting of the features, and then we set a threshold, and everyone that is above the threshold is going to be accepted. Okay, we analyzed these policies and saw some links to the gradients between gradient and EMC. Why did we do that? Because what you do with a parameterized policy, if you want to find a utility maximizing policy, is to run a policy gradient algorithm to find the optimal policy. And so we are always taking steps in direction of the gradient. And we can see here that the gradient is actually linked to the expected marginal contribution, which in turn is linked to meritocracy. So that's kind of promising. Right. So we found that for separable policies that we analyzed, but not for threshold policies. There it's a bit open. So then we went ahead and looked at a case study for college admissions in Norway. So we had a real data set of applications and to all study programs in Norway over 4 years, and the exam results of the students that were admitted. From that, we built a simulator because we needed counterfactuals, right? We need to know what's the study success of students that weren't admitted, if they were admitted, basically. So we generate what we call a realistic population of applications and study results, including counterfactuals. We set up a utility of the decision maker that is in particular not linear, just to make things more interesting. So it's a log linear function. So the way we can interpret it is that we took 3 mandatory courses within one study program that kind of reflect different disciplines in that study program. And this would be then a decision maker that wants students to be successful across disciplines. So a bit of a balance of where the success lies in student population. And we introduced a cost just to regulate that we don't admit too many students, basically. We also looked at an extra constraint of epsilon parity for gender to make things more interesting. Okay, so kind of running out of time, just maybe a very briefly for our experiments, we tested separable linear policies. We compared them to just purely going by Shapley values, the threshold policy, a greedy algorithm where we basically just sequentially take or accept students that seem to be promising in terms of utility. So that gives us the, kind of a local criterion, and a uniform policy where we just give everyone the same chances. Okay, so what we can see is that the separable linear and greedy policies perform actually quite well, not just in terms of utility, but also in terms of deviations from our stability criteria. And so that's shown on the left-hand side, where we have this unconstrained problem, so where we didn't introduce this epsilon statistical parity. We can see here that threshold policies are actually not performing too great, in particular in sense of utility, but also in meritocracy. Why is that? Because basically we're, with threshold policies, we're very limited in which kind of policy we can take. So we're limiting or restricting the policy space so much that we can't perform well anymore. And then just to keep it short, basically by adding extra constraints that prevent us from being purely utility maximizing, really, things get much more messy and we get much lower utility and much higher deviations from meritocracy. Okay, so just as the main takeaway, we defined a new notion of merit that was dependent on policies, that is the expected marginal contribution. And we rated that back to policy gradients for some policy structures. We defined a notion of meritocracy or meritocratic policies, which we again linked back to our measure of merit, the MC, and showed some properties of this. And in our case study, we found that maximizing utility can be quite aligned with satisfying meritocracy. But we do get deviations from meritocracy if we add extra constraints in our optimization problem, in particular here, parity constraints, and also if we restrict the policy space too much. Okay. So what can we do in future work? We could look at meritocracy together with other fairness notions. So here we introduced statistical parity, and we saw that this didn't really quite work well. What happens to other notions of fairness? That would be an interesting question. Also, a characterization of the EMC would be interesting for pure theoretical purposes, I guess. And what personally I find the most exciting is to look at an extension to matching problems. So we defined meritocracy now for a set selection, but in particular for the use case of college admissions, we've seen a couple of talks where this is actually a matching problem. So how could we define meritocracy here? Right, thanks.
Let's take maybe one or two questions and then take the rest offline so that everyone has.
Yeah, I'm around on the coffee break, so if anyone wants to talk to me.
Hi, thank you for your talk. I had a quick question about the results on the previous slide. Particularly on it looked like for some of the methods, the variance was really high for
Right.
dev local, but not as much for dev swap. I was wondering if you have any intuition for that.
Yeah, right, the variance looks higher. So we only did averages over 5 repeats, just because it's quite computationally heavy. So that could explain it, yeah. Right.
Hi, it was a very interesting talk. Can you say a little bit about the prediction method that you use to predict the student success, or?
Right. Yeah, we built a model. So basically, we built this simulator for generating the study population and the study results, and we take that as our ground truth. But then we did build a predictor, just a kind of simple one, to simulate how the decision maker would basically predict what the study results would be, right? Because they need to go by expected utility over some probabilities of success. Yeah. Yeah.
Thanks.
Yeah.
Hi, thanks for this talk. If I understand you correctly, this is a pretty unusual definition of meritocracy in that my merit depends on the applicant set, who else wants to go to the university.
Right.
But the utility that you just wrote down here, I don't think depends, at least to a great degree, on other students. So how should I think about how different your notion of meritocracy is from a notion of meritocracy where students have some individual merit that is independent of the other individuals that this school could select?
Right. I mean, here it does depend a bit on the. So you see that it depends on the study success of the individuals, and we want to. So we have a log linear function. We want students to be successful in all disciplines. So basically, if we have already selected students that are super successful in the one discipline, adding another one that would be very successful in that discipline would not add much utility. So in that sense, it does introduce some dependency. Yeah.
And so I just wonder if that wasn't in here, how different would the
Right.
allocations look?
Oh, right. So if it was just a linear function, basically, okay. Interesting question. Not quite sure, but I think it makes it computationally much easier to compute. Right.
Yeah, I just wonder, if a university actually did this, would this actually change which students are being admitted
Right.
to these universities in Norway?
Right. Yeah. Probably. Yeah. Yep. Thanks.
Yeah, thanks everyone for coming to the session. It's time to go on break, but let's thank the speaker first.